Hey everyone, we're beginning a new chapter now. We are moving on to chapter 4 to learn about exponential and logarithmic functions. So our first chapter is going to be 4.1 on exponential functions. So this is going to be a new class of functions for us. So here's an example. We have f of x equals 2x. So these kinds of functions are functions whose equations contain a variable in the exponent, and we can see here that our variable is x. And so the difference between these exponential functions and like our normal polynomial functions is that here we could see that a small change in the variable is a dramatic change in the function value. So notice how quickly our values increase. So we have f of 3 is 2 to the third, which is 8. F of 10 is 2 to the 10, which is 1,024. And f of 30 is 2 to the 30, that big long number. So comparing this to like g of x equals x squared, where g of 30 is just 30 squared, which is 900. So comparing these, there's a really stark difference. Alright, and then for when we have irrational powers like 5 to the square root 3 or 2 pi, where these are like our x values that we're plugging in, we approximate x basically by rational numbers. So we basically just are going to round square root 3, and we end the repeating we end the non-repeating decimal by rounding. The same thing with pi, we would just say it's 3.14 to approximate it. Okay, so for exponential functions, the exponential function f with base b is defined by f of x equals b of x or y equals b of x, because our f of x and y are the same. Where we have that b is a positive constant other than 1, so we have b is greater than 0, and b is not equal to 1, and our x is in the reals. So your book uses a for the base, but I like to use b because base b starts with the b, but it's the same thing. And additionally, for when I was talking about approximating x by rational numbers, usually those are like the ones that we use the calculator for, but I'll show some examples of that. So some examples of exponential functions are things like 2x, where our base is 2, 10x, we have base 10, 3x plus 1, we have our base is 3, and then 1/2 x minus 1, our base is 1/2. So these are some non-examples of exponential functions here. We have f of x equals x squared. Our variable is a base, not an exponent, so it's not exponential. We have g of x equals 1x, which just equals 1, basically, because whatever x value you plug in, you're going to get 1. So that's just a constant function. We have negative 1 to the x. So our base has to be a positive number, because we have b is greater than 0. And this is because we can, if you plug in, or if you have negative 1 as a base, this can result in some non-real numbers in the range. For example, if we had x equal to 1/2, it would be like negative, the square root of negative 1, which would be I. And we don't want complex numbers in our range. And then another non-example is j of x equals x to the x. So the variable is both the base and the exponent, and we just want the variable to be the exponent. So evaluating exponential functions. Okay, so we have let f of x equals 3 to x and evaluate using a calculator. So I'm going to go ahead and do that on Desmos. Okay, so if you don't have a graphing calculator, you can go ahead and use Desmos. So here I am on Desmos, and then you go ahead and go to Scientific Calculator, And then let's do our example. So I have 3x, and I'm evaluating each value here, A through C. So I have 3, and I click this to the 5th, and that's 243. And then I'm going to do negative 2/3, but make sure that your negative is in the parenthesis because it's negative 2/3. So I have negative 2/3. And then I get, oops, the parenthesis on the outside, and I get 0.4807. And I'm going to go ahead and round to that. Then our next value is pi. So I get 31.544, and I'm going to round that. And then our next example is the exponential function f of x equals 42.2 to the 1.56x models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 4 hours? So I'm going to be plugging in, because we are interested in the amount spent after 4 hours, we're going to substitute 4 for x and evaluate the function. So I have 42.2 times 1.56 to the 4. Okay, so I get 249.9256, and I'm rounding to the nearest dollar, so that rounds up to 250. Exponential function f of x equals 42.2 times 1.56x models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 4 hours? So we would be plugging in 4 for our x to find the average amount spent. And then we do this on Desmos, and it's approximately $250. Alright, so now we're going to look at graphing an exponential function. So we have our f of x equals 3x, and then we also have g of x equals 1/3 x. So here we can just plug in our values. So we have 3 to the negative 3, 3 to the 0, 3 to the 1, and so these are just powers of 3. And then the same thing for 1/3, we're just plugging in these powers and evaluating. So 1/3 to the negative 3, that's basically flipping your fraction and then raising it to the third power. 1/3 squared is 1/9. So then we graph our points and notice the differences between these two graphs. So we have g of x equals 1/3 x. It actually equals 1 over 3x, right, when we're distributing the x to the denominator and the numerator. And then I could bring the 3 up and then make the exponent negative. So I have 3 to the negative x, which we notice is actually f to the negative x here. Because if I plug in negative x to our f of x, I get 3 negative x. So our graph of g is actually our graph of f reflected across the y-axis. And so it's just basically reflected. Okay. And then notice that the graph of y equals 3x approaches, but it never touches the negative portion of the x-axis. So the x-axis, this here, or y equals 0, is a horizontal asymptote. And then our range here is a set of all positive real numbers. We never go below this axis, so we always have positive real range. Real range positive. Okay. So here in figure 2, which is this picture down here that I'll talk about. So we have graphs of family of exponential functions f of x equals b of x. for various values of our base b. So notice how all of them pass through the point 0, 1, because b of 0 equals 1 when b does not equal 0. So notice that there's two kinds of exponential functions in this figure. We have when our base is between 0 and 1, so a fraction basically, the exponential function decreases rapidly. So what this means is that the value of y decreases as the value of x increases. And then if b is greater than 1, our function increases rapidly, so our value of y increases as the value of x increases. So we could see that here we have on this side is when b is greater than 1, and then on this side we have 0, b, 1. Okay. So we could see how when b is greater than 1, our function is increasing. So it's going up as our x values increase. So as we're going right, we're also going up. But then for the fraction, the 0, where b is greater than 0 less than 1, the exponential function decreases rapidly. So our value of y, it's going down as x increases. So the more we go right, the more our y value decreases. So here we see when b is greater than 1, bx approaches 0 as x approaches negative infinity. And when b is between 0 and 1, our bx approaches 0 as x goes to infinity. Okay. So some more about our graphs. We have our exponential function, f of x equals bx, where b is greater than 0 and b is not equal to 1. So this has domain of the real numbers, and our range is from 0 to infinity. So we have the line y equals 0. The y-axis is a horizontal asymptote of f, and the graph f has one of the following shapes. So we'll go ahead and highlight this. So exponential functions have domain real numbers and range from 0 to infinity. So basically, the range is our positive reals. So here's some images. So we always pass through the point 0, 1 on just a standard exponential function. And then we have our domain is the real numbers, and our range is from 0 to infinity. And the line y equals 0 is our horizontal asymptote. Oops. Okay. So this is just a little chart to easily recall the characteristics of exponential functions. So we have our domain and range, what we discussed, passing through the point 0, 1. So our y-intercept is 1, and we don't have an x-intercept because our horizontal asymptote, y equals 0. And then we compared when b is greater than 1 and b is between 0 and 1, that the graph goes up right, and it's an increasing function when b is greater than 1, and if b is between 0 and 1, it goes down to the right, and it's a decreasing function. And then we'll discuss later that b of x is 1 to 1, and it has an inverse that's a function. And then also we know that y equals 0 is our horizontal asymptote. Okay, for this example, we're going to find the exponential function f of x equals b of x, whose graph is given. So for our first graph, we have our point 225. So we can notice here as f of 2 equals b squared equals 25. So basically when we're plugging in 2, that's going to be plugging in 2. And then we know that this is supposed to equal 25. So therefore, we know that our base is b equals 5 because 5 squared equals 25. So f of x equals 5x. For our second graph, we're doing the same thing. So we have f of 3 equals b cubed. And we know that equals 1/8 because that's our y value. So our base would need to be 1/2 to get, because 1/2 cubed is 1/8. So f of x equals 1/2 to the x. Alright, here we have some transformations of exponential functions. So we're going to go ahead and use the graph of f of x equals 2x to sketch the graph of each function. And then we're going to state the domain, range, and asymptote. Alright, so for our first one, our g of x, we have 1 plus 2x. So our first step is we're going to start with f of x equals 2x. So here I have y equals 2x. I have the points here from f of x equals 2x. So these are our old x and our old y values. But for a, we're shifting up 1 unit. So we're basically adding 1 to all these to get our new y values. And we don't do anything to the x, so we keep our x values. So basically, I'm just moving all the points up 1, so I'm shifting up 1. Okay. And then for b, we have h of x equals negative 2x. So we start with 2 of x, and then we're reflecting across the x-axis because we have our negative on the outside to get h of x equals negative 2x. And here it's just we're going to be multiplying our y values by negative 1 because we're flipping across here, the x-axis, the reflection. So basically our x values stay the same, our y values are the ones that change. So we're going to basically change all these here. We're going to keep our old x, but our new y, multiply old y by negative 1. And that'll give us our points. Oh, and then for part A, our domain we know is the real numbers, and then our range is going to be from 1 to infinity because we shifted up 1. So the line y equals 0 is a horizontal asymptote. For the example we just did, our domain is the real numbers, and our range is going to be from negative infinity to 0 because we're basically on the bottom part of our axis. So we're never going to cross y equals 0, so we're not going to have positive range values. Okay, then part C, we're going to start with f of x equals 2 of x. We're going to shift right by 1 unit to get k of x equals 2x minus 1. So this part is telling us to shift right. So basically, we're going to take our old x and add 1 to each value. And then we're going to keep old y values. Okay, so we basically we just take these old x values and we add 1, and then we keep our old y's, and then we get the graph of y equals 2x minus 1. So we see that our domain is the real numbers, and then our range is still going to be from 0 to infinity, and we have y equals 0 as our horizontal asymptote. Alright, now we're going to talk about some compound interest. So exponential formulas help us to learn about this. So we have that our compound interest is interest that is computed on your original investment as well as on any accumulated interest. So basically, if I have some amount of money, P, called the principal, so I have just any amount of money, and that's like what I start with. And I'm going to invest it like in a bank, and they have an interest rate R. And our interest rate is going to be percentage, but we represent that in decimal form per time period. Then after one time period, the interest is P of R, because my interest rate I multiply by the amount of money, which is my principal. So the interest that I accumulate is P of R, and the amount A of money is this. So I have in my account what I started with plus interest, and then I get my amount. And then here I just factor the P out. So that's for one time period. So the amount after another time period would be A equals P times 1 plus R times another 1 plus R, because that's another time period added. And then that's 1 plus R squared. And this pattern just keeps on following till we get A equals P of 1 plus R times T, or how many times periods we have. Okay, so this leads us to our formula for compound interest. And this is calculated by the formula for n compounding periods per year. So I have A of t equals P times 1 plus R over n times nt. So our A of t is the amount after t years. P is our principal, or what we start with. R is our interest rate per year. And then N is the number of times interest is compounded per year. And T is the number of years. So basically, with compound interest, if I start with a principal amount and say my compound interest is compounded twice a year, so semi-annually. So that means halfway through the year, my interest is calculated based on my principal. But the next time, like at the end of the year that my interest is compounded, it's going to take into account not only the principal, what I started with, but what got added the other time that my interest was applied. So it's just like interest that keeps building off of each other, basically. Okay. And so these are typical plans which interest is paid more than once a year in this chart. So we have semi-annually, quarterly, and monthly. And we have our n values for those. Okay, so let's go ahead and do an example. So we have a sum of $1,000 is invested at an interest rate of 12% per year. So I'm going to go ahead. So we have 1,000, so that's like our P, at an interest rate of 12% per year. We want to find the amounts in the account after 3 years if our interest is compounded annually, semi-annually, quarterly, monthly, and daily. So we're going to use our compound interest formula with P equal to 1,000, R is equal to 0.12, and T is equal to 3. So basically our n values are going to differ. So here we have our chart. So annual, the n is going to be 1. So we plug everything to our formula and we solve and we get 1,404.93. Semi-annual, our n is going to be 2. And we have 1,000 times 1 plus 0.12 over 2, 2 times 3. And that's 1,418.52. Quarterly, our n's 4, monthly, n's 2, and daily, our n is 365. And so these are our values after 3 years. Okay, now we have annual percentage yield. So our annual percentage yield is a simple interest rate that pays interest only on the principal, not on accumulated interest like compound interest. So here we earn the same interest as compound interest after 1 year. Okay, so here's an example. We're going to find the annual percentage yield for investment that earns interest at a rate of 6% per year compounded daily. So basically we have after 1 year, the principal P will grow to, we have, if we're doing our compounded interest, we have our A equals P, which is 1,000. Oh, no, just kidding. We don't have a P. Our P is just P. We have 1 plus 0.06 is our rate per year compounded daily. So we're going to divide by 365 because it's compounded daily. And then it's multiplied by 365 and then it's 1 year. And so we get P times 1.06183. So our simple interest formula is A equals P1 plus R. So we see here that our 1 plus R is 1.06183. So we can see that our R is going to be 0.06183. So our annual percentage yield is going to be 6.183%. And that's basically what our simple interest is going to be. So we're going to earn the same interest as compound interest after a year when we are doing 6.183% interest. Okay, and so it's basically taking out the compounded daily amount to it. So it would be like saying if we had our principal, we multiplied, basically just at the end of the year, we just multiplied by 6.183. We don't compound daily like the compound interest. Then we would get the same amount if I had a principal and I just multiplied it by 6.183%. But at the end of the year, I didn't compound daily. Then I'm saying that that's going to be the same as when if I had the principal and I compounded daily at a rate of 6%. Then those values would be the same. Okay, I'll stop here and I'll continue the next video with chapter 4.2. See you there.